Special cases of compound inequalities. Our objectives today are to represent intervals using interval notation, write, solve, and graph compound inequalities, and use compound inequalities to solve real-life problems. Please recall, when graphing on a number line, we use an open circle if it is not equal to, so your symbols will be less than or greater than. We used a closed circle if it is equal to, so you notice the line underneath your less than or greater than symbol. Some examples of inequalities are listed below. You can see the inequalities listed in the first column. The interval notation is listed in the second column, and the graph is listed in the third column. Recall that a compound inequality is an inequality formed by joining two inequalities with the word and or the word or. The word and tells us to look for the intersection numbers that are solutions of both inequalities. The word or tells us to look for the union numbers that are solutions of either of the inequalities. In this first example, we are given two graphs of inequalities. So we have a graph that is going from negative infinity to 4. Notice that these are parentheses because it never approaches 4 and we don't know what negative infinity is. The same thing is true for this graph below it. In our interval notation, we use parentheses because it does not ever touch the 6 and we aren't exactly sure what the negative infinity is. You can see the word and is where the shading is overlapping, or is where any part was shaded. Looking at the next example, we have two additional graphs. We have another graph that goes from 3, not including 3, to negative infinity. You notice we use our parentheses in our interval notation. The bottom graph is going from 5, but not including 5, to positive infinity. And is where the shading is overlapping. So if we took these two graphs and placed them on top of each other, they would never overlap. So we refer to that as an empty set or no solution. Or is where these two graphs, any part of these two graphs is shaded. So we can see that it was shaded from 3 to negative infinity, from 5 to positive infinity, and we use this little U-shaped symbol in our interval notation to notate that it is an OR problem. Looking at this next example, we're given two additional graphs of inequalities. The first one is going from 6, not including 6, to negative infinity, so we use our parentheses and interval notation. The bottom graph is starting at 2, but not including 2, and going to positive infinity. If this was an AND problem, we are going to look where the shading is overlapped. And if we put these two graphs on top of one another, our graphs would overlap from 2, but not including 2, so we use a parenthesis, to 6, but not including 6, so again, we use a parenthesis to notate our open circles on our graph. If this was an OR problem, we would be looking for any part that was shaded. So if we were to place these two graphs on top of one another, our entire number line would be shaded. So we would say all of the numbers on the number line, which we write as negative infinity to positive infinity, and we use parentheses because we aren't exactly sure what those numbers are. So let's try an example on our own. It says solve and graph each compound inequality, write the answer in interval notation. So when we solve an inequality, we are just getting x by itself. But remember, if we divide by a negative, we need to flip our inequality symbol. So when we divide by -2, -4 divided by -2 is 2. Flip our inequality symbol over because we divided by a negative, and then we can graph this portion of our problem. So we have a boundary point at 2, we have an open circle because it is just, there's no line underneath it or equal to. We want to put a number smaller than 2 and a number larger than 2 on either side. And then our statement is saying 2 is greater than all the other numbers. So all the other numbers that are less than 2, we would shade to the left. Looking at the next part of the problem, we have 0.5. So if we divide by 0.5, we would get x is less than or equal to 6. So on the middle number line, we want to use 6 as our boundary point. We want to put a smaller number to the left, a larger number to the right. This one we're going to have a closed circle because it's an or equal to. And our statement reads, x is less than or equal to 6, so all the values less than or equal to 6 would be to the left. When we put this on the number line, we need to account for both boundary point numbers. So we need to for sure have 2, 3, 4, 5. We also need 6. Include one number on either side of those. 2 was an open circle, and we shaded to the left. 6 was a closed circle, and we also shaded to the left. We then want to take a look at, because it was an and problem, where these two overlap. So because our 2 is an open circle, we don't want to include 2, but we want all the values to the left of that. So writing in interval notation, we are approaching negative infinity, so we use a parenthesis instead of a bracket. 2 is not included, so we use a parenthesis as well. Looking at example 2, to get x by itself, we're going to subtract 1. It's the inverse of addition. We are going to divide by 2 because it's the inverse of multiplication, so we get x is less than 2. We know that this is an open circle because there's no or equal to under it. When we proceed to the graph to graph this, we're going to place a 2 as a boundary point, 3 is a point larger to the right, 1 is a point smaller to the left. We want an open circle on 2, and we want all the values that are smaller or less than 2. Looking at our other equation, we know we're going to have a closed circle. When we solve for x, the inverse of positive 3 is negative 3. When we divide by a negative 2, we need to flip our inequality. So we get x is now greater than or equal to negative 3. On our second number line, we need negative 3 as a boundary point. To the left, we need a number smaller, which is negative 4. To the right, a number bigger, which is negative 2. We have a closed circle on negative 3 because our inequality has a line under it and is or equal to. And all the values bigger than negative 3 are to the right. On our bottom number line, we want to make sure and graph both of these on the same thing. So we have negative 3. We need to go up to positive 2. Go one past that number, one smaller than negative 3. On negative 3, we wanted all the values greater. On positive 2, it was an open circle, and we wanted all the values less than. So because we have an or problem, we are just looking to satisfy one of our inequalities, so we could go from negative infinity to positive infinity, or our solution could be all real numbers. Looking at our last and final example, I just want to notate that my first problem is going to be an open circle. My second problem is going to also be an open circle. I want to take note that this is an and problem, so it must satisfy both inequalities, or overlap is the area we are looking for. So when we solve for x in our first inequality, the inverse of positive 5 is negative 5x. The inverse of -2 is +2. The inverse of multiplication is division, so we get x is less than -1. On our number line, our boundary point is -1. Number bigger to the right is 0, smaller to the left is 2. We said we had an open circle. If we want all the values that are less than -1, we shade to the left. Looking at the next example, I'm going to move my -5x by adding it, just so I don't have to remember or divide by a negative. So I flip my inequality. Add my 5. So I get 15 is less than 3x. Inverse of multiplication is division. 5 is less than x. My boundary point is a 5, a number bigger is 6, a number smaller is 4. We said it was an open circle. 5 is smaller or less than x, so we want all the values this direction. On our number line, we want to start with our -1 because it's the smallest. We want to make sure and get all the way to 5, and then put one number past 5, one number before -1. At -1, we had an open circle and it's shaded. To the left, at 5, we had an open circle shaded to the right. Remember, though, we wanted an and problem, and they have to overlap. There is nowhere on this number line where these overlap, so we say it is no solution. It is an empty set. And in interval notation, we can just use this circle with the line through it to notate